Hi everybody, Mrs. Pesic here.
And Miss Bella here.
And we're looking at section 9-1, Introduction to Sequences. The objectives in this section are to find the nth term of a sequence, write rules for sequences, and your vocabulary is sequence, infinite sequence, recursive formula, term of a sequence, finite sequence, and explicit formula. And this is the first section in a chapter that we're looking at on sequences and series. So a sequence is an ordered set of numbers. Each number in the sequence is a term of the sequence. So if we have a sequence like 1, 2, 3, 4, 1 would be the first term, 2 would be the second term, 3 would be, oh, that's pretty obvious. Okay, so a sequence may be an infinite sequence that continues without end, such as the natural numbers, or a finite sequence that has a limited number of terms, such as that last sequence that we just looked at.
You can think of a sequence as a function with sequential natural numbers as the domain and the terms of the sequence as the range. So let's just kind of clarify what we're saying in that case. So the values in the domain are called the term numbers and are represented by n. So if this is a table here of what we had, n stands for the term. So the first thing, second, third, fourth, fifth, so on. The term value, we're going to say that is a sub n is what those values would actually be. So in this case, my term values are 1, 1, 2, 3, 5. Instead of function notation, such as a of n, sequence values are written using subscripts. So the first term is a sub 1. So in this example above, we would say a sub 1 is equal to 1, a sub 2 in this case is also equal to 1, a sub 3 equals 2, and so on. Whenever we get to the nth term, if it went on forever, that would be a sub n. Because a sequence is a function, each number n only has one term value associated with it, so a sub n. So again, all that's telling us in this case is that since we know up above, a sub 4, for example, is equal to 3, a sub 4 will never equal any other value besides 3 in this type of problem because it is a function. So one thing in the domain has one value in the range. And just a little reminder here, when we are reading math, a with the subscript of n, we read that as a sub n.
All right, so the Fibonacci sequence, which was invented to describe a rabbit population, is the following: 1, 1, 2, 3, 5, 8, 11, 19, and so on. The first two terms are 1, and each term after that is the sum of the two terms before it. So let's make sure we're understanding that. So the first two terms are 1, and then you would add those terms together to get 2. Then you'd have to add 1 and 2 together to get 3, add 2 and 3 together to get 5, and so on. So this can be expressed using this rule, that a sub 1 is equal to 1, a sub 1 is equal to 1, a sub 2 is equal to 1, and then a sub n is equal to a sub n minus 2 plus a sub n minus 1. This, a sub n minus 2, means two terms back from your current term, and a sub n minus 1 means one term back from your current term, where n is greater than or equal to 3. This is called a recursive formula. A recursive formula is a rule in which one or more previous terms are used to generate the next term.
Okay, not that it matters, but when I made these notes, I made a typo and it's going to bother me. Really, 5 plus 8 is not 11. 5 plus 8 is 13.
That's 21.
That's 21. Okay, that looks better.
I'm glad that you fixed that up, Miss Bella.
Yeah, it wouldn't have mattered for the explanation, but that would have bothered me that I can't add two numbers. Okay. So let's do some examples here. So example 1, we want to find the terms of a sequence by using the recursive formula, which means you will rely on a term before it to find the answer for the term you're looking for. So we're going to find the first 5 terms of the sequence with a sub 1 equals negative 2, so that's the first term. And to find each of the following terms, a sub n, you'll do 3 times a sub n minus 1 plus 2. Again, all this part right here, a sub n minus 1, just means the term previous. So one term before it is what you'll be using. So let's list them out. A sub 1 was given to us, and that is equal to negative 2. For our second term, a sub 2, it's going to be 3 times, again, if I look right here, n minus 1. Well, if I'm on my second term, that would really be a of 2 minus 1, or really just a of 1, which is just what I had right there. So negative 2 plus 2. So using my whole formula that we were given. So that would be negative 6 plus 2, which is equal to negative 4. For a sub 3, I'll say 3 times my previous term, so 3 times negative 4 plus 2 is negative 12 plus 2. This answer is negative 10. a sub 4, 3 times my previous term, which is negative 10 plus 2, so negative 30 plus 2, where we have negative 28. And a sub 5 will be 3 times negative 28 plus 2, which is going to give me negative 76 plus 86 plus, oh wait, 84 plus 2 equals negative 82. So our first 5 terms, negative 2, negative 4, negative 10, negative 28, negative 82.
All right, so that brings up your first notes must do. You're going to find the first 5 terms of this sequence. The sequence starts with the first term, a sub 1, being negative 5, and then the next term, a sub n, is going to be a sub n minus 1 minus 8. So you take your previous term minus 8. That's your first notes must do. Okay, in some sequences you can find the value of a term when you do not know its preceding term. An explicit formula defines the nth term of a sequence as a function of n. In other words, you can find the 10th term directly just using a formula. You don't need to have the 9th term to find it. All right, so finding terms of a sequence by using an explicit formula. Find the first 5 terms of this sequence, a sub n equaling 3n plus 1. So a sub 1 is going to be 3 to the first minus 1, which is 3 minus 1 is 2. A sub 2 is going to be 3 to the second minus 1, which is going to be 9 minus 1, which is 8. A sub 3 is going to be 3 to the third minus 1, which is 27 minus 1 is 26. A sub 4 is going to be 3 to the fourth minus 1, which is 81 minus 1, which is 80. And a sub 5 is going to be 3 to the fifth minus 1, which is 243 minus 1, which is 242. So the first 5 terms in this sequence would be 2, 8, 26, 80, and 242. This was using an explicit formula.
We're going to do one more example with an explicit formula here. And again, we do not need to know the previous term, so very similar to the example, the first example there, I guess this would really be maybe 2b. We'll figure out what it is by just using what n value we're at. So a sub 1 is going to equal 1 squared minus 2 times 1, which would be 1 minus 2, or negative 1. My second term, a sub 2, is 2 squared minus 2 times 2, which will give us 4 minus 4, or 0. A sub 3 is 3 squared minus 2 times 3, or 9 minus 6, which is 3. A sub 4 would be 4 squared minus 2 times 4, or 16 minus 8, which would give us an 8. And finally, a sub 5, 5 squared minus 2 times 5, which would give us 25 minus 10, or 15. So our first 5 terms of this sequence, negative 1, 0, 3, 8, 15.
Okay, so remember, linear patterns have constant finite differences. We've looked at finite differences in the past. Quadratic patterns have constant second order differences, and exponential patterns have constant ratios. So let's take a look at this example. We're writing this rule for the sequence. Write a possible explicit rule for the nth term of the sequence that goes 5, 10, 20, 40, and 80. So if we try to find out what the constant, what a finite difference is here, if we take the difference, 80 minus 40 is 40, 40 minus 20 is 20, 20 minus 10 is 10, 10 minus 5 is 5. It looks like the first order differences are not equal to each other. If we tried the second order differences, we'd get 20, 10, 5. Those are not equal either, but notice that for each one of these, the ratio, not the subtraction, but the ratios are going to be equal. So if I take the 40 and I divide by the 20, I get 2. Same thing if I take the 20 and I divide by 10, I will also get 2, and the 10 divided by 5 is equal to 2. So what we notice is that we have a constant ratio of 2 for each one of these, and since we have a constant ratio, that must be an exponential pattern. So if it's an exponential pattern, then we're going to be able to find this by saying, in this case, that ratio is going to be 2 raised to some power, so 2 raised to the n, for example. And then we have, if it's 2 raised to the n, if it's 2 raised to the first, that's equal to 2. If it's 2 to the second, it's 4. If it's 2 to the third, it's 8. But we weren't getting 2, 4, and 8. We were getting 5, 10, 20. And really, let me back this up a little bit and say we really could have started with 2 to the 0 is 1. So instead of 1, 2, 4, 8, we had 5, 10, 20, 40. So what would we have to do to each of these numbers here to get 5, 10, 20, 40? Well, it looks to me like we would just need to multiply each of these by 5. So that makes me think that our pattern is really not just 2 to the n, but it's going to be 5 times 2 to the n, but actually we need to do 2 to the n minus 1, because our first term was not 2 to the first, it was 2 to the 0.
All right, let's look at another one of those for finding the rules for our sequence. Okay, again, we want to find explicit, which means it will not rely on the prior term. I just plug n in and get my answer here. So first thing we're going to do is let's start off with the finite differences again. So 11.5 minus 9 is 2.5. 9 minus 6.5 is again 2.5. Looks like we're in good shape here. Again, 2.5, and again here, 2.5.
You lucked out, Miss Bella. You got a nice linear one.
I did. I got the easy one here. So since the first order is the same, that means that my explicit formula for this one, or my explicit rule, must be linear. So my n value that I'm going to plug in will be raised to the first power when I use this. I won't need a quadratic or anything squared. So in order to do this, what I'm going to do is I'm going to figure out what is my starting point. So I want to always kind of know what is A1. What is your first term? So my first term in this case is 1.5. Now, when I have my 1.5, I need to know what would I have to do to it to get to my next term to get to 4. Well, in this case, I'm going to add on, I guess maybe difference, we want to call it common difference. So what was the same between those? Well, my common difference, if I add on, is 2.5. Now, I want this rule to fit any of them, or any of my terms here. So I'm going to add on 2.5 how many times? Well, to go from the first term to the second term, so a sub 1 to a sub 2, I have to add on 2.5 once. To go from to get to the third term, I should say, from the first term, which is always my starting, I would need to add that on twice. To get to the fourth term, I would have to add that on now 3 times. So hopefully you're seeing that whatever n value you're at, you need to add on 1 less of that same number of the 2.5 added on. So again, I have my starting point, and then this is my common difference. I'm going to add on 1 less than the term I'm on. So when I have a sub 1, if I put a 1 minus 1 in here, that would be a 0. So for my first term, a sub 1, that would give me a 0 here, and that would give me my just 1.5, my starting point. So to clean this up just a little bit, my formula, if I distribute this 2.5, will be 1.5 plus 2.5n minus 2.5, or my rule can be 2.5n minus 1. So that is the rule that you can now plug in any n value and get out what you would have for this sequence. You can even test that by maybe plugging in 3, 4, 5 and make sure you get those values.
Is it okay to just leave the formula, just a sub n equaling 1.5 plus 2.5 times n minus 1?
Yeah, I think that's fine.
Because I like that better.
Yeah, leave it like that then.
Okay, and if we just test this one, if we just try a sub 5, then that would be 1.5 plus 2.5 times 5 minus 1. That's 1.5 plus 2.5 times 4. I need to do my multiplication first, so 1.5 plus 10, which gives me 11.5. Was that our 5th term of the sequence?
Yes, it was.
Awesome.
All right, so here's your second must do. We'd like you to give it a try writing an explicit rule for the nth term of the sequence. So again, to start off, find your differences and see if it is the same. Are they linear? Maybe second order differences, are they quadratic? And then create that rule for us using n to find the rule for a sub n. All right, and that ends our notes for this. So thank you for watching.
And we'll see you next time.